we have been discussing thin film dynamics, and in the context of that we have seen what are the simplified governing equations in a non-dimensional form, and we have started looking into simplified boundary conditions. First the kinematic boundary condition we have seen in a non-dimensional form, and next the logical extension will be to look into the tangential force balance and normal force balance in a non-dimensional form. So, tangential force balance, tangential force balance, how you do it? So, you have the traction vector So, this you have to keep in mind that these are dimensional parameters to begin with, and we will convert this into non-dimensional expressions. So, now we will write an expression for the S vector. So, we have already written an expression for the n vector, or even if we have not written it, we will write it. We have written it implicitly, because if you recall that we have constructed a function f is equal to y minus h, which is a function of x and t. So, grad f this grad f, why it is calculated in the context of S and n? It is calculated in the context of n because grad f by definition gradient of a function is a vector which is normal to the graphical representation of the function. So, if f is a function, then its gradient is a vector which is normal to the function f drawn in a suitable plane. So, grad f will be in a direction of n. So, that is the first thing. So, now you write this as this one, and we can write this in terms of the corresponding dimensional parameters. So, this will have a dimension characteristic dimension of h naught, and x has a characteristic dimension of LC. So, h naught by LC so this means epsilon h naught by LC is epsilon. So, minus epsilon del h del x I plus j. Okay. So, if that be the case, what is a normal vector, unit normal vector? So, this is in the direction of n. So, this is grad f by mod of grad f. This is a unit vector in the direction of grad f, or unit vector in the direction of the interface, normal to the interface, basically unit vector in a direction normal to the interface. So, grad f is along the interface, therefore sorry, f is along the interface, therefore grad f is normal to the interface. So, this will be now if you see, so in the denominator there will be epsilon square this square plus 1. So, it will be minus epsilon del h del x I plus j divided by square root of epsilon square right. So, clearly the leading order term is 1 right, this is leading order term as compared to this. So, this is as good as in the leading order. So, we are writing everything in the leading order. So, this is as good as minus epsilon del h del x I plus j. So, if this is n, what is s? So, let us say that the curve is such that this is s, this is the tangent to the curve and this is n. Angle between s and n is 90 degree. So, this let us say this angle is theta. So, s, remember this is the unit vector, so its length is 1. So, s you can write cos theta I cap, this is x and this is y, plus sin theta j cap, resolving this one vector unit vector in along x and y. If that be the case n, so this angle is what? This angle is 90 degree minus theta. So, n is minus cos 90 minus theta, that is minus sin theta I plus cos theta j, right. Therefore, n is minus sin theta I, so this is sin theta and this is 1 is cos theta, right. So, s is cos theta I, that is I plus sin theta j plus epsilon del h del x j, okay. So, we have by some exercise obtain what is n and what is s, and this is very important because that will be necessary for evaluating these dot products. So, our next endeavor will be to evaluate those dot products. So, now what is T? Remember that this is by Cauchy's theorem. So, here we will apply this same Cauchy's theorem, but in a 2 dimensional framework. So, this will be tau xx, tau xy, tau xy, tau yy into nx ny, where nx is minus sin theta and ny is cos theta. So, it will be a vector with 2 components. So, this is tau xx nx plus tau xy ny, this is the x component of the vector and tau xy nx plus tau yy ny. So, because these are all dimensional parameters, I will prefer to give a dash for everybody. Now, tau xx, all these things, let us look into these terms. I mean, before just blindly writing the terms, we can clearly assess which one is greater as compared to what. So, tau xx 2 mu, this one, tau xy and tau yy okay. So, tau xx into nx, nx will be minus sin theta. So, epsilon del h del x, right, nx is minus sin theta. So, minus epsilon del h del x, right. So, this is, let me write it somewhere. And ny is 1, right. So, if you multiply this with epsilon del h del x, already there is a term of the order of epsilon, and here there is a term which is of the order of 1. Now, you cannot conclude anything from this, because first you have to transfer these to non-dimensional terms and see what is the order itself of this term. So, that we will do now. So, 2 mu UC by LC, this is mu UC by H naught plus VC by LC and this is mu Vc by H naught So, clearly all these terms will have a coefficient which is of the form of some velocity by some length, because we already do not know which is what. We definitely know that Vc is of the order of epsilon uc, that much we know. So, that much we know. Now, looking into these terms, first of all look at these multipliers. I do not want to really write it here and make it long, but we will just observe the terms and try to see which one is important and which one is not. So, let us say that this term tau xx is multiplied with nx. So, this, when it is multiplied with nx, there will be an order of epsilon, right. On the top of that there is some multiplier. When tau xy is multiplied with ny, this term will also be of the order of epsilon, because this is of the order of epsilon and ny is 1, but this is clearly not of the order of epsilon. So, this has a velocity by a small length, right. uc is the dominant velocity and this is the smaller length scale. Out of h naught and LC, h naught is smaller. So, uc by h naught will clearly dominate epsilon uc by LC, right, because uc by h naught will be greater than uc by LC and epsilon is will make this term further less, right. So, this term will clearly dominate, and in terms of tau xy, so tau xy nx, again when you multiply with nx, you see that there is nx already has epsilon. So, this term whatever it is multiplied with epsilon, it will become of the order of epsilon. So, that will be less than as compared to this term in this box, and tau yy ny. So, tau yy ny is so tau yy you can see clearly you have a epsilon order. So, out of these 1 2 3 4 except for this term, others will have of the order of epsilon or epsilon square, right. This will be therefore the leading order term. So, this will be in the leading order, I am writing again it is in the leading order. So, this term, this dominating term in tau xy, so this is mu uc by h naught okay. Now, we have to make a dot of this with S. So, when you make a dot of this with S, I dot I will become 1 and J does not feature. So, this I will have a dot product with this I of S. So, it will be mu uc by h naught del u del y, okay. See, I mean this we have done rigorously, but if you just do it from an intuition that this is the tangential stress. So, this is like mu du dy, you can argue that why it should be du dy, because the interface is now curved, it is not flat. See, although interface is curved, in the leading order its deviation from flatness is not that significant, and therefore, in the leading order it is effectively like mu du dy, okay. Next what we will do is, next we will calculate the right hand side. So, this surface gradient operator grad S. So, what is that? So, this is this one, right. So, better write with dash, because these are dimensional derivatives. So, now first of all we will operate this with S. So, now this dot S is as good as S dot this. So, look into one thing, when you make S dot of with this, you will have a S dot with this minus S dot with n. S dot with n is 0, because S and n are orthogonal to each other, they are perpendicular to each other. That is how S and n are defined, you can see S and n are perpendicular to each other. So, this will boil down to right.
It should be written like S dot grad operator.
Yes, yes, S dot grad. Because this is an operator, this should be operating on this, right. So, you can follow how this is written. Out of this we are only having this term retained, because this n dot with s, this n dot with s will actually be 0. So, this will be eventually s dot with this one. So, now we have to calculate. So, let me erase the upper part of the board to free some space. So, S dot this one. So, S is I plus epsilon del H del x j, that is what is written in the right side of the board. You can see dot of and sigma dash you can write as sigma into sigma 0, where sigma 0 is the reference surface tension coefficient. So, that makes sigma a non-dimensional surface tension. So, this is a dimensional reference surface tension parameter, and therefore, this is a non-dimensional surface tension. So, this in this way we are transforming a dimensional surface tension to a non-dimensional surface tension sigma via a reference sigma naught. So, this sigma naught. So, you have del x prime plus del y prime right. Now, x prime is equal to x into LC. So, this you can write as 1 by LC y prime is y into h naught. So, epsilon by h naught So, epsilon by h naught is 1 by LC. So, you can take 1 by LC as common. So, this will be sigma 0 by LC into this operator operating over sigma. So, this operator we call as del tilde. So, this del tilde is defined as del x plus del y into del h del x. Okay. So, this now we can write this expression as mu u c by h naught okay. So, you can write del u del y is equal to h naught by L C, which is epsilon divided by mu u c by sigma 0 into this one. This mu u c by sigma 0 is a very important non-dimensional parameter. So, you can write this as follows. So, I am cleaning this part of the board a little bit and writing it here, mu u c by h naught. So, you can write this as mu u c by sigma naught, mu u c by h naught, this is shear stress times an area, and this is sigma 0 into A by h naught, where A by h naught is a characteristic length. So, this is shear stress multiplied by area. So, this is viscous force, and this is surface tension coefficient times length. So, this is surface tension force. So, this is called as capillary number. Viscous force by surface tension force. Okay. So, you come up with the final non-dimensional form of the boundary condition. Okay. So, this is regarding the tangential force balance. In the next lecture, we will see how to write the boundary condition for normal force balance in a dimensionless form. Thank you very much.